This is the first of 2 videos for SLO6, Discrete Probability Distributions, and today we're going to look at section 6.1, Random Variables. Now remember, last time we discussed a little bit about the normal distribution, that unimodal, symmetric, bell-shaped curve. We're going to save that for next SLO and instead focus on the more discrete probability distributions. And in particular, we're going to look at random variables. Now recall that a variable is a characteristic whose label or value may vary, right? It's just something about an individual that could vary. A little bit of terminology here. A random experiment, situation where unknown results occur. Each unknown result is a separate outcome. Set of all outcomes is the sample space. And a subset of the sample space is called an event. Not sure that one's listed in the book, but I've heard it before. So, poker player shuffles a deck, draws 5 random cards. What's the experiment? I should say, what's the random experiment? What's the sample space? The random experiment is, pause the video, see if you can get it. The drawing of 5 random cards. The sample space, and maybe I should say 5 random cards from a 52 card deck, I guess, if we want to be precise, right? We should add that, right? The sample space is the set of all 5 card. Now you could either say collections, all collections of 5 cards, or if you want to be fancy, you could say all 5 card poker hands, right? Just because a hand is a set of 5 cards, right? It's just 5 cards. So the set of all 5 card hands is the sample space. Now a random variable is a numerical outcome of a random experiment. Discrete, we're going to recall this from way back earlier, I think SLO1. Discrete random variables can be listed. Continuous variables, not so much, right? They can assume every value in an interval. This week, we're going to focus on discrete random variables. When we turn to the normal distribution next week, that's when we'll get into more continuous stuff. So let's consider a random experiment. Right, an individual flips a fair coin 3 times, right? What are all the possible outcomes and their probabilities? And what I'm assuming, by the way, is that you're familiar with the concept of a probability. If not, then you can look in chapter 5 in the book, but we're going to be skipping it. So if you think about it, there are 8 outcomes. All heads. There's 1 tails, there's 1 tails, there's 1 tails. I guess you could have 2 tails, 2 tails, 2 tails, and I guess you could also have 3 tails. Let's try that again. Right, and that should be 8 different outcomes. Now, what's the probability? Well, the probability of getting 3 heads in a row, we should all know that it's 50%, or 1 out of 2, to get 1 heads. And these coin flips are what we call independent. So we'll say each coin flip is independent of the others. What? Meaning they don't affect each other. right, for independent events A and B, we know that the probability of A and B equals the probability of A times the probability of B. And so that's what we're going to do here, right? The probability of getting a heads is 1 and 2. And they're all independent. So we just multiply each of those by each other. And we get 1/8. And if you notice, the probability of getting tails is also 1 out of 2. So actually, if you think about this for a bit, the probability of all of these events, all these outcomes, it's going to be the same. It's 1/8, right? All of them. Next up, a probability distribution is a list of probabilities for each value of a random variable. Now note that we must be talking about a discrete probability distribution. In our case, if we're really just going to list them, if we can actually list them out, then it's discrete. You can totally talk about the probability of a continuous random variable, but you can't really list the probabilities. You just need to sort of understand what they are. And you can still illustrate them, you can still analyze them and everything, but you can't physically list them all. Now, really quickly, we're going to let P of little x denote the probability of a random variable having the value little x. I've seen it written in other textbooks as if you let just to be clear, big X be or if you say let X is a random variable, and then you say P that big X equals little x, probability of a random variable big X having the value little x. I find that to be a little confusing and a little bit confusing to say, so I'm going to use the blue notation. I think that's what the book does as well. Okay. Just so you know, though, in case you ever see another stats book. So anyway, a couple things that we should know. Probabilities are always between 0 and 1 inclusive. Probability of 0 means it never happens. Probability of 1 means it always happens. We should know that the probability of all the events equals 1, and I guess we should say assuming x1 through xn are all the outcomes. All right. So for example, let's find the probabilities of a couple of events, right? Each of these is an event. The probability of at least one heads. Well, the probability of at least one heads equals the probability of one heads plus the probability of two heads plus the probability of three heads, right? All of these are mutually exclusive. It means you can't have one head and two heads, can't have two heads and three heads, etc. So you can just add up their probabilities. I'll state that down below in a sec. Right, but what's the probability of getting one head? Well, we can just kind of look at them, right? Probability of getting one head is, I guess that's 3 out of 8. Probability of getting two heads is, I guess, 3 out of 8. And the probability of getting three heads is 1 out of 8. Right? Now, I guess we could have just looked and said, well, and how many of these events do we have at least one head? And that's just 7, right? Maybe that would have been easier. Let's try doing that for number 2, right? Probability at most one tails. Well, how many cases do we have at most one tails? I think it's just these guys. So we say probability at most one tails equals 4 out of 8, better known as 1/2. Probability of 2 heads, well, I think we already kind of did that. 3 out of 8, right? Again, that's these guys. Probability of exactly 2 tails, well, you could probably, again, it's the same as the probability of 1 heads, right? Which is 3/8, right? Exactly 1 heads, that is, right? And then the probability that we get at least 3 tails. Well, let's not very exciting, right? It's just the one case, right? All right. Now note that the events, let's say, I guess we could say, I'm trying to think of I guess we could say these guys, yeah. Note that the events 2 heads and 2 tails are what we call mutually exclusive, which means they can't both happen at the same time. Well, I'll just say they can't both happen. Right? You can't get 2 heads and 2 tails in this experiment. Okay? So in general, if A and B are mutually exclusive, then the probability of A or B equals the probability of A plus the probability of B. This works only if they're mutually exclusive, right? That's what we did up here. Also, 2 events A and B are complements. That's complements, not compliments. They're not saying something nice about each other. Now you could think of this 2 ways. Number 1, well, I guess you really need both of these. Number 1, they have nothing in common, right? They have no outcomes in common. And then number 2, their union equals the sample space. Right? As in they complete each other. When their powers combined, they equal the sample space. Okay? So in other words, this occurs precisely when the probability of A, that's an A, plus the probability of B equals 1, or the probability of B equals 1 minus the probability of A. So it's kind of nice if 2 events are complements, because if you know one probability, the probability of one of them, then you know the probability of the other. So for example, 2 events that are complements, I believe the first and the last are here. Yeah, at least 1 heads and at most 3 tails are complements. Show it. Now, it's not enough just to say that their probabilities sum to 1, which of course they do. You have to show that you get one precisely when you don't get the other. Okay, so I'll leave that to you. Now we can view, here's one of the cool things about probability distributions. We can view a probability distribution as a description of a population. In that for each x, for each value x, the probability P of x represents the proportion of the population with value x. So for example, all right, relax. We have 1,676 people. How many hours per day they were able to relax? We're given a frequency table, right? Now we're going to assume that the 1,676 people here are a population, okay? And we're letting our random variable, big X, be the number of hours of relaxation for a person sampled, right? Now, you can view this, like you can view this as a frequency table, whatever, but what you can also do, if you go into Minitab and you enter all the data in, you can get proportions, and you can say, okay, well, what proportion of the people relaxed 0 hours or 1 hour, etc. And you can think of these as population proportions, but you can also think of it as, well, what's the probability if I choose a person at random that they will have been able to relax 3 hours, right? That's the probability is the same as the proportion of the population. So let's see if we can get the frequencies. We're going to store the result in variable probability. And let's see, the expression is going to be each frequency divided by 1676. Let's see if that gives it to us. There you go. So maybe we could work on rounding. I'm not sure how nicely it'll round for us, but whatever. Those are our results, okay? So that was a nice little way for Minitab to calculate the probabilities just so we didn't have to, right? Again, all we did was we divided each of these frequencies by 1676 and we got the probabilities. Okay. Something to keep in mind. So construct the probability distribution of X. Well, thank you, Minitab. We just did that. Can I? Oh, yes, it's going to let me do that. Now, of course, if I ask this on an assessment, then you are more than welcome to do this. Let's get that up and running. Oh, a little big there. Okay, so that's part A. Find the probability that a person relaxes more than 4 hours a day. Be a little careful with the wording of these problems, right? More than does not mean at least. It means more than, like this, right? So we want to do probability that we relax for greater than 4 hours is going to equal, maybe we could say the probability that X is greater than 4 is going to equal, looks like it's 0.138, I'll just do it to the nearest thousandth, right? Plus 0.089 plus, well, that's a 9, just to be clear, plus 0.020 if we round, plus 0.036. And whatever that equals. We can just do this on the side. No need to bother Minitab with this, but of course we could if we had to. Right, 3, 2, 13, 15, 18. So I think I'm getting 283. No, maybe I'm wrong. That was back of the envelope, but I think that's right. Okay. Find the probability a person doesn't relax at all. That's pretty easy, right? We already know that. It's a probability that X equals 0, and that's just 0.068. Right? Done. This guy. Okay. All right. Now, one of the most important measures in statistics, the same way that the mean or the average is one of the most important descriptive statistics, the expected value of a random variable is correspondingly one of the most important measures of statistics as well. You could think of it as the measure of center of a random variable. So suppose that we have a random variable, big X, and it can have values little x1 through little xn. Right? It's finite, right? And each value has the respective probabilities, these guys, right? The expected value of big X is the value. Now we write this as mu X. That's a big X, just to emphasize, big X. And that's going to equal x1 times the probability of x1 plus x2 times the probability of x2, etc., plus xn times the probability of xn. Move that down a little bit. You also might see it in the book written like this. That's all fancy and stuff. Now, the expected value can be viewed as the mean in a certain sense because the formula is literally a weighted average. We didn't actually get into what a weighted average meant, but you can check the book if you're interested. So if we say find the expected number of hours people relax, well, let's use our trusted mini tab. Hopefully this will work, right? So we go to calculator. And this time we'd like to store it in variable expected value. And what's going to be the expression? Well, it's just going to be, the expected value formula. So we're going to do sum, capital sum, parentheses. And I'm hoping we should be able to do just the value times, maybe I'll just press the times button, times the frequency, times the probability, I lied. All right, that should give it to us. So what that's going to do is it's going to do C1, it's going to do 0 times the probability of 0, right? Plus 1 times the probability of 1, plus 2 times the probability of 2, etc. And it should enter it all in that. Look at that right there. 3.36217. All right. So what that says is that we would expect, well, let's see what that means there, right? Let's get this in there. 3.36. So I guess I'll just say 0 times, let's see, what do we have there? 0.068 plus 1 times, I'll just write the first couple out. 0.111 plus etc. plus 8 times, what was that? 0.036. Equals 3.36 hours. Now, what does this mean? So does it make sense to view this value as a mean number of hours people relax? You can pause this a minute and think about it. But yes, it does. Yes, we could say each probability can be viewed as a proportion of the population of 1,666 individuals that were studied. So 3.36 hours is the mean number of hours rested per day yeah, I'll just say that, right? So that's what we have. Right? If you added up the number of hours for all the number of people who slept those hours and then divided by 1676, you'd get the same thing. Okay? Now, analogously, we can find the standard deviation of a random variable. Right? Now, as with the mean, right, we need to know its probability distribution, right? Now, the formula for the variance and standard deviation is as follows. I'm going to write the old formula, or sort of a version of the old formula. So I'll write it as sigma x squared. And this is going to be, well, let's see, we should remember this is going to be x, oh, I guess it's going to be x1 minus mu x squared times p of x1, the probability of x1, plus blah, 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 plus xn minus mu x squared times the probability of xn. Right? And then you might see this written as the sum of x minus mu x. Just to be clear, this is a big X, and that was small x squared p little x. And then you have then that sigma of, again, that's big X equals the square root of, well, I guess I should write the whole thing. You know, I'm just going to write this. I'm just going to write sigma squared X, right? Right. So it's the square root of all that, right? So say this is the standard deviation. Oh my gosh. Of the random variable X. Just want to make sure that that's big X. Now it turns out an equal and easier formula is as follows. Sigma squared. I'll do the sigma squared first because it winds up being I could even show this to you in class or on a separate video. It wouldn't take very long. It winds up being x1 squared p of x1 plus blah 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 plus xn squared times p of xn, and it winds up being minus the expected value squared. And so sigma of, again, that's big X equals just the square root of all that, right? Okay. So let's see. Find the variance and standard deviation. Just I can find the variance, whatever. So let's see if we can do this using Minitab, right? I guess I call this standard deviation. Let's make that the variance. Let's just do that, okay? So let's see if we can find the variance. So we go to calculator. Now we're going to store this one in, let's say, variance. Let's do the variance first. And then this is going to be, let's see, what is it going to be? The sum of, so we know that it should be the value squared times the probability. All right, so we're going to go to value. And we're going to caret 2. And then times the probability. And then we have to do minus, and then it's going to be the mean squared. Now, what do we say the mean was? I think 3.36. So I'm just going to do 3.36 squared. Let's see if that gives it to us. No, so that's the variance. Okay. And so the standard deviation is just going to be the square root of that. All right, so we go to calculator. All right, and we do that. Oh, darn it, my bad. Huh. Little technical difficulty there, right? Let's get rid of this square root. Let's find that variance again. Okay, and then calculator. One thing I forgot to do, store this in standard deviation, and now we take the square root. There we go. There we go, right? So there you have it, all right? I'm just gonna, and I do want to actually get this in the calculator too, right? I want to show you how we did that, right? Let's just crop this super quick. Actually, let's just have all this right here. And then maybe we'll have this guy. And we're going to crop this as well. Okay, and that's how we get it. And that's all we've got. Thanks.